The Blind Watchmaker by Richard Dawkins. Picture yourself strolling along a beach. You spot a stone and pick it up. It's smooth, worn down by countless waves, but honestly, it's just a stone. You toss it back without a second thought. It's been sitting there forever, sculpted by the mindless push and pull of the ocean. Now imagine that same walk, but this time you find a watch half buried in the sand. Everything changes, right? You'd brush off the sand, feel its weight in your palm, watch those tiny gears spinning behind the glass. There's zero chance you'd think, oh, this just happened. You'd know instantly that someone, a skilled watchmaker, carefully designed and assembled every piece. The complexity screams intention. Every spring and gear whispers purpose. Back in the early 1800s, a theologian named William Paley built an entire argument for God's existence on this exact comparison. He basically said, look around you. Check out the human eye. It's 1,000 times more intricate than any watch. It's got a lens that focuses perfectly, an iris that adjusts to light, a retina that captures images. If a watch needs a watchmaker, doesn't the eye need a divine designer? For generations, this argument felt bulletproof. I mean, just look at the natural world. Bird wings seem custom-built for flight. Fish fins look tailor-made for water. Flower petals appear perfectly designed to seduce bees. How could all this jaw-dropping precision be anything but intentional? Here's the kicker, though. It's not. Today we're diving into one of the most mind-bending ideas in human history, brilliantly laid out in Richard Dawkins' bestseller, The Blind Watchmaker. This book doesn't just explain evolution. It completely dismantles the notion that complexity requires a conscious designer. What emerges instead is a universe without a blueprint, yet somehow filled with its own stunning magnificence. Dawkins takes us on a wild ride to crack the ultimate mystery, how we got here. By the time we're done, you'll understand how something as breathtakingly complex as your own eye could arise from the simplest beginnings, with zero foresight, zero planning, and zero designer. You'll discover the single, elegant process that's the real watchmaker of life on Earth, and you'll learn why that watchmaker is completely, utterly blind. Let's zoom in on that human eye for a second, because the complexity is genuinely staggering. This isn't some basic camera we're talking about. Inside each of your eyes right now, roughly 125 million light-sensitive cells called photocells are hard at work. These cells connect to about 3 million ganglion cells that start processing visual information before your brain even gets involved. Now let's go deeper. Take just one of those 125 million photocells. Inside that single cell, you've got these tiny chemical factories called mitochondria, each one juggling hundreds of different substances. There's a nucleus containing a digitally coded database that holds more information than all 30 volumes of the Encyclopedia Britannica combined. One cell. And you've got about 10 trillion of them in your body. When you're staring down that level of mind-melting complexity, Paley's conclusion feels almost inevitable, right? This couldn't possibly be an accident. Our brains are basically hardwired to see design and complexity. We see a car or a smartphone, and we know an engineer sweated over every detail. Our entire world is packed with planned, purposeful objects. Why should living creatures be any different? This gut feeling, as compelling as it is, leads us completely astray. And this is where most people stumble when they think about evolution. They jump to the conclusion that the only alternative to an intelligent designer is pure, dumb luck. They picture evolution as a tornado ripping through a junkyard and randomly assembling a Boeing 747. The odds against that are so ridiculously astronomical that it's basically impossible. And you know what? They're absolutely right. It is impossible. But that's not what Darwin's theory actually says. Evolution isn't a theory of random chance. It's a theory of cumulative selection. And that one word, cumulative, changes absolutely everything. Let me show you what I mean with a clever thought experiment Dawkins created using a computer program. Imagine a monkey sitting at a typewriter. We want it to type a line from Shakespeare, Methinks it is like a weasel. The keyboard has 26 letters plus a spacebar, so 27 characters total. What are the odds our monkey types this phrase correctly on the first try? The chance of getting just the first letter right, that capital M, is 1 in 27. The chance of nailing the first two letters, M and E, is 1 in 27, times 1 in 27. The chance of typing the entire 28-character phrase correctly is 1 in 27, multiplied by itself 28 times. That number works out to roughly 1 in 10,000 million. In other words, it would never, ever happen. Not in the lifetime of the universe. That's pure single-step chance. That's your tornado in the junkyard. And that's absolutely not how evolution works. Now let's tweak the rules just slightly. This is where things get fascinating. We'll program the computer to start with a completely random string of 28 characters, just like the monkey did. Let's say it spits out something like WDLMNLTDTJBKWIRZREZLMQCOP. Here's the twist. Instead of wiping the slate clean and starting over, the program makes multiple copies of this phrase, but with a few random errors or mutations thrown into the copying process. The computer then compares all these new, slightly mutated phrases and picks the one that most closely resembles our target phrase, methinks it is like a weasel. Maybe the winning phrase in Generation 2 is just barely better, WDLTMNLTDTJBSWIRZREZLMQCOP. Still complete gibberish, but it's got one more correct letter than before. This new phrase becomes the parent for the next generation. Rinse and repeat. Copy with random errors. Select the best match, over and over and over. How long does it take to hit the target now? After just 10 generations, the computer produced MDLDMNLSITJISWHRZREZMEXP. After 20 generations, Meldon LSITISWPRKEZWECSEL. By 30 generations, Methings ITISWLIKEBWECSEL. And in just 43 generations, boom, the computer nailed it. Methinks it is like a weasel. What would have taken longer than the age of the universe with single-step random chance took only moments with cumulative selection. Each individual step was still small and random, but the selection of which steps to build upon wasn't random at all. It was guided toward a target. Now, in real biological evolution, there's no distant target, no finish line that nature is racing toward. The selection is just brutal, simple survival and reproduction. But the principle holds. Small, gradual changes, when they stack up one on top of another, can climb mountains of improbability and create absolute wonders of complexity. This is the beating heart of the blind watchmaker concept. Evolution builds complexity, not in one spectacular leap, but step by tiny, incremental step. And at no point does it need to look ahead, plan for tomorrow, or have any kind of goal in mind. So how does this whole process even get off the ground? For cumulative selection to work, you need a few basic ingredients. You need something capable of making copies of itself, what we call a replicator. You need those copies to occasionally have small, random errors or mutations. And you need those replicators to have some kind of influence over their own chances of being copied again. Today, the main replicator is the DNA molecule. DNA is genuinely spectacular information technology. The DNA packed into a single one of your cells contains enough information to store the entire Encyclopedia Britannica 3 or 4 times over. It's a digital code with a 4-letter alphabet, A, T, C, and G. This information is essentially the recipe for building a body. And the accuracy of DNA's copying process is mind-blowing. The genetic message has been passed down through billions of copies over millions of years, with a precision that makes our best technology look clumsy and amateurish. There's a particular gene called the histone H4 gene that's almost identical in cows and pea plants, even though their last common ancestor lived over 1 billion years ago. But the very first replicator on Earth probably wasn't anything as sophisticated as DNA. It had to be much simpler, something that could arise spontaneously from the raw chemistry of the early planet. Chemist Graham Cairns-Smith has this fascinating theory that the original replicators might have been inorganic crystals in clay. Think about how a crystal grows. In a solution, atoms lock into an orderly, repeating pattern. A crystal basically acts as a template for its own growth. And crystals can have imperfections. When a crystal with a particular pattern of flaws breaks apart, the pieces can act as seeds for new crystals, each one inheriting the parent's pattern of flaws. Now imagine different types of clay crystals competing. Some types, because of their particular structure, might break apart more easily or get spread more effectively by wind as dust. These successful crystals would automatically become more common. This is a very simple, low-tech form of cumulative selection in action. Cairns-Smith suggests that these early mineral replicators began using organic molecules like RNA as tools to help them replicate more efficiently. But once RNA, a new and improved self-replicating molecule, came into existence, a new and much more powerful kind of cumulative selection could really get rolling. The new organic replicators were so vastly superior that they eventually took over completely, discarding the original mineral scaffolding, which has now vanished without a trace. This idea of a genetic takeover is brilliant. It shows how a high-tech system like DNA could arise from incredibly simple, non-living beginnings. The crucial insight is that you don't need a miracle to kickstart the process. All you need is a basic replicator, any replicator at all, that makes occasional copying mistakes. Natural selection handles the rest, automatically. Once this engine of cumulative selection gets humming, it doesn't just build simple things. It can construct systems of absolutely breathtaking complexity. And one of the most powerful forces driving this is something we see constantly in the human world: the arms race. Think about a cheetah and a gazelle. Cheetahs that are faster with sharper claws are more likely to catch gazelles, survive, and have cubs. So over generations, cheetahs tend to get better at hunting. But this means the environment for gazelles is getting progressively tougher. Gazelles that are faster and more alert are more likely to escape cheetahs and have fawns, so gazelles get better at escaping. What you've got is an escalating spiral. Improvement on one side drives improvement on the other. This is a positive feedback loop. Each side is running as fast as it possibly can just to stay in the same place. Biologist Lee Van Vallen called this the Red Queen effect, after the character in Through the Looking Glass, who has to keep running just to stay put. This is why there's a progressive quality to evolution. It's not because life is striving toward some predetermined goal. It's because the enemies of any given species, its predators, its prey, its parasites, are themselves evolving and improving. The weather doesn't get systematically worse year after year, but your enemies absolutely do get systematically better. This relentless evolutionary pressure is what has forged the incredible weapons and defenses we see throughout nature: the eagle's razor-sharp vision, the viper's deadly venom, the bat's sophisticated sonar. Speaking of bat sonar, it's genuinely a marvel of engineering that would make any human designer weep with envy. Bats hunt in total darkness, navigating and finding tiny insects using ultrasonic clicks and their echoes. The underlying math is similar to radar, but the execution is on an entirely different level. When a bat is just cruising around, it sends out about 10 clicks per second. But when it locks onto an insect, the click rate can skyrocket to 200 pulses per second, faster than a machine gun, giving the bat a real-time, high-definition image of its twisting, turning target. The bat's cry has to be incredibly, almost unimaginably loud, because the echo bouncing back from a tiny fly is extraordinarily faint. The intensity drops off with the fourth power of distance. But this creates a massive problem. How does the bat's exquisitely sensitive ear avoid being completely deafened by its own ear-splitting shout? The solution is elegant. The bat has tiny muscles in its ear that contract just before it sends out a pulse, effectively switching the ear off for a split second. Then they instantly relax to maximum sensitivity, just in time to catch the faint returning echo. It's a perfectly timed send-receive switch, technology that our own radar engineers had to painstakingly invent from scratch, but which bats perfected millions of years before humans even existed. But perhaps the most dramatic and seemingly extravagant products of evolution aren't the weapons of an arms race at all, they're the ornaments of sexual attraction. Why does a peacock have such a magnificent yet obviously burdensome tail? Darwin himself was genuinely puzzled by it. The tail doesn't help the peacock survive. In fact, it's a massive handicap, making the bird much easier for predators to catch. Darwin's answer was the theory of sexual selection. He realized that survival is only a means to an end, and that end is reproduction. If a long, brilliant tail makes a male more attractive to females, the advantage he gains in mating can completely outweigh the survival disadvantage. The peahens, in a sense, act like human breeders, selecting for aesthetic qualities. But this just pushes the question back one step. Why should females have these seemingly arbitrary preferences? Why would they prefer a trait that's actively bad for survival? The brilliant biologist R.A. Fisher provided the answer, and it's another story of explosive positive feedback. His idea, later developed mathematically by Russell Land, works something like this. Imagine an ancestral bird species where, just by random historical accident, a slight majority of females happen to have a mild preference for males with slightly longer than average tails. Now, a female who chooses a long-tailed male will have sons who inherit their father's long tails. But here's the crucial part. She'll also have daughters who inherit her preference for long tails. What's more, because of this dynamic, the genes for long tails in males and the genes for preferring long tails in females tend to get linked together in the gene pool. A male carrying long-tail genes is also likely to carry the unexpressed genes for preferring long tails, which he inherited from his mother. Now the self-reinforcing spiral kicks into high gear. When a female chooses a long-tailed male, she's not just choosing good looks. She's unknowingly choosing genes that will make her own daughters prefer long tails too. The genes for the preference are, in effect, choosing copies of themselves. This creates what Fisher called a runaway process. As tails get slightly longer, the female preference for even longer tails gets slightly stronger. This makes tails get longer still, which makes the preference even stronger. It's an explosion. Tail length shoots up, getting more and more exaggerated, until it's only stopped by severe counterpressure from natural selection, the point where the tail becomes so cumbersome that males simply can't survive at all. This runaway process explains the almost absurd beauty of the peacock's tail, or the bird of paradise's plumes. They weren't designed for survival. They're the products of an evolutionary fashion trend that spiraled into explosive, self-sustaining feedback. This brings us to our final piece of the puzzle. What about the pace of evolution? One of the most common objections you hear about evolution concerns the gaps in the fossil record. If evolution is truly gradual, why don't we see a smooth, unbroken chain of fossils from one species to the next? The theory of punctuated equilibria, proposed by Niles Eldredge and Stephen Jay Gould, offers an elegant explanation that fits perfectly within Darwinian thinking. They suggest that the gaps aren't just missing data or poor record-keeping. They're real. They reflect how evolution actually unfolds. Think about how new species typically form. Most often it happens when a small, isolated group gets separated from the main population, perhaps by a new mountain range or river. In this small, isolated population, evolution can happen much more rapidly. Genetic changes spread quickly through a small group, and the selection pressures might be quite different from the original habitat. Meanwhile, the large parent population back in the original homeland might not change much at all. It remains in what paleontologists call stasis, basically just hanging out unchanged. Now imagine you're a paleontologist digging for fossils millions of years later. Where are you most likely to dig and find fossils? In the large central area where the parent species lived for a very long time. There, you'll find fossils of the same species, layer after layer, showing very little change over long periods. Then, suddenly, in a higher, more recent layer, you find fossils of a new species that evolved in that small, isolated pocket somewhere else entirely. To you, the paleontologist, with your incomplete sampling, it looks like a sudden jump, a punctuation in the record. The transition from one species to the other seems to be completely missing, but it's not really missing. The gradual evolution absolutely did happen. It just happened relatively quickly, and in a completely different geographical location. What you're seeing in your local fossil record isn't the evolution itself, but rather the migration of the new species back into the old territory after it evolved elsewhere. The progress of evolution isn't like a slow, steady crawl at a constant pace. It's more like long periods of relative stability, punctuated by brief, rapid bursts of change. But even these rapid bursts are still gradual, step-by-step processes, perhaps taking tens of thousands of years. They only seem instantaneous when viewed against the vast backdrop of geological time spanning millions of years. So when we put all these pieces together, what picture emerges? We have a world absolutely teeming with life, of staggering complexity and diversity, and at the heart of it all lies a single, astonishingly powerful process. Not a designer with a cosmic blueprint, not pure blind chance throwing dice, but a blind watchmaker, methodically building without seeing. It's a process of cumulative selection, working on replicators that make occasional copying mistakes. It works step by microscopic step, building complexity over immense stretches of time that dwarf human comprehension. It's driven relentlessly forward by the pressure of evolutionary arms races, and sometimes sent spiraling into beautiful extravagance by the unpredictable whims of sexual selection. It leaves behind a fossil record that's not a smooth film reel, but rather a series of snapshots, recording a story of long, quiet periods punctuated by moments of creative revolution. This process has no mind and no mind's eye. It has no purpose, no ultimate goal, no vision of the future. It is the blind watchmaker. And it's the only explanation we've ever discovered that's powerful enough, in principle, to explain the existence of you and me and every living thing on this planet. When you truly internalize this idea of the blind watchmaker, it fundamentally changes how you see everything around you. It doesn't strip the world of wonder, despite what some critics fear. Actually, it does exactly the opposite. It infuses everything with a deeper, more profound, and more authentic sense of awe. Think about it. Every living thing around you right now, the tree outside your window, the bird singing on its branch, the intricate network of veins visible on the back of your own hand, is the end product of an unbroken chain of successful ancestors stretching back billions of years. That's genuinely breathtaking when you let it sink in. Each and every one of your ancestors, all the way back to the very first microscopic replicator, was good enough at the game of survival to live long enough to reproduce. They navigated their world successfully, escaped their predators, found food, attracted mates, and passed on the instructions for building the next generation. Trillions upon trillions of other lineages failed and vanished. Only a tiny, triumphant fraction succeeded against overwhelming odds. And we're their descendants, carrying their legacy in every cell. That, to me, is a far more humbling and magnificent story than any ancient creation myth. The most powerful lesson from the blind watchmaker is its direct assault on our intuition. Our brains evolved to understand the world on a distinctly human timescale. We think naturally in minutes, days, and years. We're built to see purpose and intentional design in complex things around us, because in our human-made world, complex things genuinely are designed. A watch really does imply a watchmaker. But the natural universe doesn't operate on a human scale or follow human logic. Dawkins teaches us to escape the prison of our own limited, familiar perspective. He invites us to think on a geological timescale, where 1,000,000 years is just a brief moment. On that timescale, The seemingly impossible becomes not just possible, but actually quite probable. The step-by-step accumulation of tiny, fortunate changes, filtered ruthlessly through the sieve of natural selection, becomes a creative force more powerful than any conscious designer could ever be. So how can we apply this monumental idea to our everyday lives? It starts with a simple but profound shift in perspective. Next time you step outside, try this little experiment. Don't just casually see a tree. Really see it as a survival machine that's been perfected over millions of generations. See its leaves as exquisitely engineered solar panels, shaped by countless iterations to capture sunlight with maximum efficiency. See its roots as a sophisticated mining operation, expertly extracting nutrients and water from the soil. See it as one living chapter in a 4-billion-year-old story, an epic tale of trial and error, of struggle and success, of death and survival. Realize that the powerful feeling of "it must have been designed" is essentially a trick your mind plays on you. It's a mental shortcut your brain takes to save processing power, and it's a completely faulty shortcut when you're contemplating the natural world. The real story of how that tree came to be is so much more interesting and remarkable than simple design. It's a story of emergence, of stunning complexity bubbling up gradually from elegant simplicity, without any grand conductor waving a baton, or any master architect drawing up plans. Understanding this doesn't somehow make life meaningless or rob it of value. It does precisely the opposite. It gives us the freedom and responsibility to create our own meaning. We're not puppets dancing in a pre-written cosmic play. We're the astonishingly, almost impossibly lucky products of a vast, unguided, and stunningly beautiful cosmic process. We're perhaps the only creatures in the entire universe who have become conscious and intelligent enough to understand the very process that created us. And that realization in itself is a truly wonderful and precious thing to be. That was a summary of The Blind Watchmaker by Richard Dawkins. We've touched on some genuinely grand themes today, but a summary is really like looking at a photograph of a mountain range. The real experience, the true sense of scale and majesty, comes from walking those trails yourself, taking your time, absorbing the details. The book is filled with beautiful analogies, crystal clear explanations, and a passionate sense of wonder that I could only hint at here in this compressed format. If any of these ideas sparked even a flicker of curiosity in you, I genuinely encourage you to pick up a copy and read it yourself. It's not just a book about biology or evolutionary theory. It's fundamentally a book about a revolutionary way of seeing the world, a new framework for understanding our place in the vast cosmos. You'll find a link to the book in the description below. Also, if this journey through one of the great breakthrough ideas of science was valuable to you, please take a moment to hit that like button and subscribe to the channel. That way, you won't miss our next exploration of another potentially life-changing book. Let's keep learning, questioning, and growing together.